In this chapter, we are going to look at something called similarity of figures. We've talked a lot about congruent figures in which two shapes are exactly the same and all of their measurements are the same. In this chapter, we're going to look at something called similarity, where there's some sort of a relationship between the two figures, but they aren't exactly the same. Today, we're not going to yet define the word similarity, but first, we're going to talk about the idea of ratio and proportion, because that's going to be an important concept in similar figures. Ratios are probably something you have encountered in another math class along the way. A ratio is defined to be a ratio of one number to another one is the quotient. What's quotient mean?
Answer to a division.
Answer to a division. So it's a division of the first one divided by the second one. There are two ways that we can write ratios. We can write them with a colon, and we read that colon as the word to. So we would say A to B. We can also just write them as a division, the first one divided by the second one, okay, as a fraction. We don't want to do a decimal here, but we can do a fraction of the first number divided by the second one, or we can do it with a colon. It doesn't matter to me which form you use. Some people are more inclined to use one than the other. Personally, if the problem starts with one notation, I tend to just keep working with that notation. And if the problem doesn't begin with any particular notation, then I kind of default to fractions. But that's just my own thing. Colons or fractions, either one is completely appropriate. So in this example, we're asked to find the ratio of OI to ZD. So what we need to do is find the length of OI, which is 14, and divide that by the length of ZD, which is 6b. A ratio should always be given in its simplified form. So we need to reduce fractions when appropriate. Again, we don't want to divide them out and turn them into decimals, but we want to reduce them out into their simplest form. So 14 and 6 both reduce by 2 to leave 7 over 3b. You could also write that in the colon notation if you prefer. 7 to 3b is exactly the same thing. And it doesn't matter to me which notation you use. The next one says find the ratio of the measure of the smallest angle of the trapezoid to that of the largest angle. So we need to know what that missing angle is, because if that angle up by O happens to be the smallest or the largest, then we actually need to be using it. So how can I find out how big that angle is? Yeah.
Add them all up and subtract it by 360.
Okay, we know that inside of a quadrilateral, a four-sided, four-angled figure, we should have 360 degrees. So we can add up what we have so far, and that adds up to 250, and subtract that out, and find out that there's 110 left over for that angle. So it turns out that angle O wasn't the biggest or the smallest, but that is something we should check, because it could have been, and then that would need to be part of our answer. So the question asks us to find the ratio of the smallest to the largest. So what's the smallest angle? 60. What's the largest angle? 120. And then we want to give our ratio in reduced form. So what does 60 over 120 reduce to? 1/2. And again, you can write it in its fraction form, or it's completely fine to write it in its colon notation as well. Questions? The measures of three angles in a triangle are in the ratio of 2 to 2 to 5. Find the measure of each angle. Okay, so we know the ratio of these, but we don't know what they actually are. That's what we're looking for. What do we know about the three angles of a triangle?
Yeah, up to 180.
They should add up to 180.
Okay.
But 2, 2, and 5, that doesn't work because that only adds up to 9. So those can't actually be the measurements. So they must have been reduced down by some factor, but we don't know what that factor is. So what we're going to do is say that that factor they were reduced down by is x, and that these angles are 2x, 2x, and 5x. Because that still has a ratio of 2 to 2 to 5. We could reduce out all those x's. Then we know that those three angles should add up to 180. When we add those all up, we get 9x. Divide both sides by 9, and we find x is 20. Always be careful when you get an x equals answer, because we tend to want to put a box around it and say we're done. But the problem says find the measure of each angle. So what do I need to do to know how big the angles are?
Multiply them.
Multiply that by what?
The original ratio.
Into the original ratio. So our angles are 2x, 2x, and 5x. So if x is 20, then our angles are 40, 40, and 100, which add up to 180 and could be reduced back down to 2, to 2, to 5. Okay. When we have a ratio of 3 items, we use the colons, not the fractions. Okay, so if there's only 2 things, it doesn't matter whether you use colons or use fractions. But if you have 3 or more items, we use the colons only. Questions? You will have problems exactly like this on your homework. Questions on this one, knowing that. Then this section in the book defines this word proportion. A proportion is an equation, so it has an equal sign that states that 2 ratios or fractions are equal. So a proportion is an equation that has a fraction equals a fraction. I don't really know why this section defined it here, because today we're going to do nothing with proportions. Tomorrow our lesson will be all about proportions, so I guess this is just a little foreshadowing that this definition showed up here. But tomorrow we will talk a lot about proportions. So some more examples with ratios. Again, in a ratio, we want to make sure that we give our answer in simplified form. So if this is our starting ratio, then what would it be when we reduce it?
3, 4. Wait, 3, 4.
What does it reduce by? 4 to leave 3/5. They both divide by 4 to leave 3 over 5. Four n over n squared. What does n squared mean?
N times n.
N times n. So then what can we reduce the top and the bottom of this fraction by?
N.
An n. And when we reduce out one n from each of them, we're left with 4 over n.
Is that it?
Mm-hmm. Question. Is the ratio A to B always, sometimes, or never equal to the ratio of B to A?
Always.
Sometimes.
Sometimes.
I heard all 3 answers.
Sometimes.
So
Maybe.
we need to work this
It
out.
is definitely
Sometimes.
sometimes.
All of the above.
No doubt in my mind.
Yes.
So when would they be the same?
When they're 4 and 4.
Like if the 2 numbers were the same, because that'd be like 1 to 1. So when wouldn't they be the same?
5 to
2 to 1, 1 to
Okay, anytime the numbers are different. 2 to 1 and 1 to 2 are different things. Okay, so the order the numbers are given in a ratio usually does matter. If the 2 numbers happen to be the same, then it doesn't really matter. Or actually, if they happen to be opposites of each other, so if it's like a 4 and a negative 4, then that's really okay, because either way that would reduce down to negative 1 and 1. But in most cases, the order does matter. So be careful in a problem if you're asked for a ratio in a specific order that you give the ratio in that specific order. Ratios are something that are actually really applicable. So a question we always get in math classes, typically when things get difficult is when are we ever going to use this? Students don't mind doing something that's easy if they don't see a purpose to it, but as soon as it gets hard, we want to know that we're doing something with a purpose. And ratios are something that has a purpose. A lot of purposes. We use them a lot in our everyday lives. So Barbara is making oatmeal for breakfast. The instructions say to use 3 cups of water with 2 cups of oatmeal. What is the ratio of water to oatmeal? The directions say to use 3 cups of water to 2 cups of oatmeal. So what is the ratio?
3 to 2.
3 to 2. She has some company coming over, so she needs to make more than usual, and she wants it to be the right consistency, not too runny, not too thick. So she's going to use 6 cups of water.
4.
How many cups of oatmeal does she need?
3. Wait, no, 4. Oops.
She doubled the water. She needs to double the oatmeal.
I'm wrong.
For the next group of problems, we're going to use a diagram.
Stop talking.
Okay, ST to DI, what would we get?
6 to 5.
First as unreduced, so what would we actually start with?
12 to 10.
12 to 10, taking the lengths of those segments. So ST is 12, DI is 10, but we always want to give our final answer in its reduced form. So what do 12 and 10 have in common?
2.
A 2 to leave 6 to 5.
Are you not allowed to use decimals?
No. No decimals in a ratio. Good question.
Have you seen school?
Yes, that's
DI to IT. What's DI?
10.
And what's IT?
16.
16. So we weren't actually given IT, but we can do like a segment addition there and say that IT is made up of IS and ST, and that adds up to 16. So we start out with 10 to 16 as our ratio. What do those have in common to reduce?
2.
A 2 to give us 5 to 8.
Such a crime.
4 to 10.
IS is,
4.
DI is,
And
IT is.
16.
You can reduce down a ratio of 3 terms if you can reduce down all of the terms. If you can only reduce down 2 of them, it doesn't work to do that. But if you can reduce all of them, you can and should. So what do those all have in common?
2.
2, and if I reduce them down by 2, I get 2, 5, and 8.
3.
What is the ratio of 750 milliliters to 1.5 liters? When we are comparing values, we need to be comparing apples to apples, so to speak. We need our units to be the same. It doesn't matter what the units are, but they need to be the same. So we need these to either both be milliliters or both be liters. I tend to think it's easier to change them into milliliters, but it doesn't really matter which way you go. So if I change them both into milliliters, how many milliliters are there in a liter?
1,500. Oh,
1,000, which gives us 1,500
Oh, I was wrong.
milliliters.
Would have had it right a second.
And what does that reduce down to?
1 to 2.
75.
1 to 2. 75 to 150. 75 goes into 150 twice. So 1 to 2 would be our final ratio there. Okay, you do not need to include units in a ratio answer. So we don't need to say it's 1 milliliter to 2 milliliters. We can kind of think of those units as reducing out of there as well, just like a variable would reduce out. If the ratio between 2 segments, when measured in centimeters, is 4 to 3, what would the ratio be if we measured them in inches?
Either like
It's 2.54 centimeters
It's 2.58, but it actually doesn't matter.
43.
4 to 3. Units don't matter in a ratio.
Oh.
As long as the units are consistent, they don't matter. Because what we would do is, to turn these centimeters into inches, we would do 2.58 times each of them. But then to reduce it out, we could just divide that 2.58 right back out of there. And we would end up right back where we started. So units do not matter in a ratio. A ratio of measurements will always be the same ratio regardless of what units we choose to use, as long as we're using the same units for both parts of that ratio. Okay? So like in the last one, we need to make sure we had the same units for the ratio, but the units we choose actually don't matter. Last set of questions here. If I know that three numbers have a ratio of 1 to 2 to 5, but I don't know what the numbers are, could the numbers be 1, 2, and 5?
Yes.
Yeah, those have that ratio. Could it be 10, 20, and 50?
Yes.
Yeah, that would reduce out. Each of them reduced by 10 to give us back to 1 to 2 to 5. About 3, 6, 20.
No.
Why not?
Because
I almost thought that.
it should be 30. No.
They don't.
It should be 15. If that last one was 15, then it would work out that each of them would be 3 times as big as the original. But that 20 didn't work out the way it was supposed to. So that answer wouldn't work. What about x, 2x, and 5x?
Yes.
Yeah, because we could reduce all those x's out of there and it would work. Okay? Your homework is from section 7-1 tonight.